Today we're going to do section 6.9. Why do I have 7 all the time? First, let's scan the book. Here we are. We have, what is this? Page 210 and 11, which we should have already done it, but I will show it again a little bit. And then the bottom. Okay, that should be it. And next, 212 and 13. Oops. Let's see. We have it right here. And okay, a little closer on top. And a little bit closer on the bottom. All right. So today we are going to do the other section 6.9, which is other coordinates. That's referring to the cylindrical and the spherical coordinates. Now before we get going, I want to show you what we learned this is from Calculus 3, okay? On page 574, what we already know from basic calculus, how to do polar coordinates. Here are all the information, and of course you can refer to the book itself too. There is not the various conversion rules for both spherical and polar coordinates, as well as how they convert to each other. That is, right here shows you how it converts from cylindrical to spherical, and that is convert from spherical to cylindrical, etc. And this is from rectangular to spherical, of course. So, and you're going to need some of this stuff in the homework, okay? So maybe you should take a screenshot of this thing for future reference. So that's that. So let's start. Page 210. First, please read this introductory paragraph yourself, and I will begin at the bottom, cylindrical coordinates, where it begins as we remember from basic calculus. X is our cosine theta, y is our sine theta, and z is just z. In this system, then, we have the region v theta r will be defined as r, and then z is the one that goes from phi to psi. Okay, as you might imagine how that is going to be defined. That where you have a cylinder and the ruling is perpendicular to the plane z equal to 0, which is the xy plane. Okay, you have all this, and then the z is the one that defines two functions that goes up and down. And we integrate over such an area in which we require phi and psi to be continuous, and phi is less than psi. So that the whole thing makes sense. So theorem 6 is similar to what we have proven in the past. That is the same as theorem 5. And what is theorem 5? Maybe we should look at it first. Let's see, where was theorem 5? No, I can't find it. Let me find it. Theorem 5 just says that the triple integral is the same as the iterated integrals, and they're both in rectangular coordinates. Now theorem 6 that we're looking at is a similar thing, except that it got changed into polar coordinates. That's the only difference. Okay, so we have we integrate over the region R, except the iterated integral is now done in the polar form, from z equals to phi to z equal to psi. And so we are not going to do the proof, being that we've done this similar proof 3 times already so far, I think. Yeah, and as said previously, so we're going to skip that, but know that it's very similar. Okay, and then the next page we have example A, which is very straightforward. So I ask you to do it yourself. I did it right here in case you want to see what I did. See, and so please do it yourself as well. The example A. So next, let's look at section 9.2, subsection 9.2 on page 211, where we are looking at spherical coordinates. Spherical coordinates, of course, have the equations x equal to r sine phi cosine theta, y equal to sine phi sine theta, and z equal to r cosine theta. And I should probably remind you that what that means. that means that right on, let's see, this side, okay, that is what is phi and all that stuff. I'll make this a little bit bigger. So phi is the angle that's measured from the z-axis, okay, and theta is the angle on the xy plane measured from the x-axis, whereas phi measures down, right? And then and r is the rho, which the book calls r, but it's actually rho, okay? And in the past, it's called rho. Rho is the distance from the origin to our point, whereas the r in cylindrical coordinates is the horizontal distance from the origin to the point. That is, if your point is up here, the r is only the horizontal distance going wherever. It doesn't go from the origin up. So that's the difference. See, in this picture, you see the difference between r and rho. In this book, however, they use r for both situations. So you have to make a distinction here, okay? And don't let yourself get confused by which one is r and which one is rho. R and rho in the coordinate system has a conversion formula. Yeah, right here in this thing, it says that to the conversion between rectangular and spherical is that r equals the rho sine phi. And if you look at the picture, you know why. Let me move this way. Yeah, see, r equals the rho sine phi. You can see it in the picture real soon why that is the case. Okay, so that's what all the angles mean. And of course, we had this before, so let's move on. And so we will have a region. The region of the integration is called V of r, g theta phi, and h theta phi. Now, what does that mean? R, in this case, means rho. That is, this r is the distance from the origin to the point directly, okay? And it's not the cylindrical coordinates. So this r going from the origin to wherever we're heading for is going to be, I should probably show you that before I say any more. And yeah, see right here from calculus 3, you notice the coordinate system for spherical coordinates it used the symbol rho, whereas this for spherical coordinates. Just want us to be perfectly clear. But the book used r, which is okay. We'll use r as well for now. But we'll bear in mind that this is spherical coordinates. So the r actually means rho at this moment. So the r then goes from the origin to wherever that is like the sphere, okay? It goes from, the r is a function that is limited by, on the bottom in the function of r equals to g of theta phi, on top by r equals to h theta phi. So, which is fine. In the meantime, the big R, the region of the base region, is the set theta phi, okay, such that phi is in between some theta functions like this, whereas theta itself is between two constants, alpha and beta. Now think about this for a moment very carefully. What does R is the set of theta phi mean? That means that R is a region that's infinite, because R is only defined by angles, okay? You can point this way, that way, whatever, but there is no distance limit to this R. So this R is different from previous R's. Previous R's, they were bounded, right? You have some kind of a thing. Doesn't matter which coordinate system. Whereas this R has no bounds because it doesn't tell you how far it has to be. It can be any distance from the origin as long as it only restricts which angle is going. So before we move on, I have plotted an example of all this stuff because this is super odd. Okay, I don't think it's anything that we have seen before. So I have plotted a sample situation of how this might work. Let's see, where is it? Here it is. So my sample is I'll follow what they said. Okay, that is we have a region here where V is equal to this thing. Okay, I'm just copying from what the book says. It's a set of r theta phi such that r is between those two functions, right? Yeah. Why do I have two of them here? I am not sure, and it doesn't matter. And then this r is the big R is the set of theta phi such that the theta and phi, and to such that phi satisfies these equations. And so we have, all right, so how might that look like? So here's what I plotted, okay? First, notice that this is theta. Theta is between two constants, alpha and beta. So I have a sample here, okay? And so that's simple enough, right? Theta is on the xy plane, and it goes from this angle to that angle. So that's that part. So this region right here is where theta varies in my sample. So the next picture, I have plotted a sample phi there. The green surface is phi equals to cosine theta, okay? The orange surface on the bottom, phi equals to, well, this is phi equal to h theta, the top one, and phi equals to, this is phi equal to g theta, the bottom one. I have sine theta plus 1 as a sample. So basically, this shows you what happens when g theta is less than phi less than h theta. So phi is varying between those two surfaces. Now, basically, what that means is that here's the region R, okay? Now, the region R is, you notice that where theta varies between alpha and beta, and with the sample which we have right here. Let's see, yeah, here's theta, okay, it varies here. And then phi is varying between those two surfaces, the green one and the orange one. So together, R is this region, as you can see. Is that odd looking thing, and it goes forever, okay? My picture stops there, but it goes infinitely in that direction. That is, the green surface will continue, and so will orange and the gray surfaces. They all continue they start at the origin, as you can see, but they go on indefinitely. So the entire R region just moves forward, and that is what's different about this system. So and then finally, you notice that we have defined that the distance, finally we got a distance in here to limit things, right? The distance will be limited by a function small g and then a function small h. Okay, so I plotted such a function here. Okay, on top here is that is the function small g, okay, which is that blue thing. So, which I made it up to be this function. It's a function of g, theta, and phi. I made something up here, and it ended up looking like that. Okay, so then that is the small one. That's the small limit. Only the part you see that's actual blue. That's the only part that matters. The rest is just sticking out. Okay, so that's the bottom limit of this region R. And then finally, I have also plotted a top surface. Here's the h theta that I made up to be, well, that thing, okay, which is end up being the round surface. You can still see the bottom function in there, the purple thing in here a little bit. But anyway, so the top surface then restricted the region so you can sort of see what it looks like. Maybe I make it a little bigger. Okay, and so as you can see, then the top surface bounds, the entire region now is closed and bounded, okay, and it doesn't go to infinity. But that's because R is, which is the distance from the origin, is the only thing that's restricting the stuff, so that the things don't go to infinity. So that now we become a piece of solid in space. So you can see what the solid looks like. Okay, it has radial lines going towards the origin, and it stops at the small g function in there, and then it goes out until it hits the orange function on top. That's h. So that is again the small function. The small g is the blue function, and towards the end there, and you can see only a little bit. The little bit that's blue that you see at the next to orange is the only bit that we care about. The rest is just extra. And the orange, it should be red, but somehow the camera is showing it as orange, which is fine. But the red picture is orange, whatever. That is only the part that's inside the region R that matters. Okay, the rest is just extra. Well, I didn't get rid of the extra stuff because it was getting too complicated. So this is just to give you an idea of what this integration solid of integration, that is, what does the v theta phi looks like. okay, and because it's odder than anything we've ever seen. So that is, so I thought that would be a nice way for you to visualize it. Visualizing is not necessary, okay, for this kind of stuff. We just imagine, the book didn't bother drawing a picture. So we can just think of it by logic alone. However, being that we do have Desmos 3D, I figure we might as well take advantage of it and visualize and enjoy the visualization while we can. Because the most we can do is visualize 3D objects. If it goes beyond that, then we can no longer visualize it. So then we're forced to use logic. So let's visualize while it's possible. Now, and in case you want to plot this yourself, okay, here are the formulas I used to plot it. And specifically, I used the conversion rules right here in order to plot this thing. Okay, once you get the conversion rules in, like for example, to plot phi equals to sine theta plus 1, you just enter phi and theta and all that stuff into the formula, which gets you this thing right here. And then you type this into the Desmos 3D. The reason we have to do this is because Desmos doesn't do spherical or cylindrical coordinates at all. Okay, I mean they do. Well, anyway, the point is you have to convert it into rectangular coordinates. But once that's done, it plots very nicely. For example, an equation like this, which is a very complicated, look at this thing, right? It's a very complicated implicit equation, and Desmos plot it without a, blink an eye. It doesn't have, it just does it instantly. That's why what we have to do is just plug the conversion things in, and it knows what to do. So that is, that's that, in case you're interested in doing this type of thing. Continuing on page 211, let's look at theorem 7, where what is this? This is just saying that the triple integral is the same as the iterated integral in spherical coordinates form. Now we have already done this in basic calculus. Okay, let me show you where I got this thing. Okay, and to refresh your memory, this is from calculus 3, where it says, remember this thing? Okay, the integral is equal to what is that? Whatever. The point is that here's the formula for spherical integrals, and what you have to do is you have to stick in a rho squared. In our case, rho is called r. Okay, and then sine phi, and then the rest kind of goes along. So the only part you have to remember is the rho squared and sine phi has to be stuffed in there. The theorem 7 says the same thing. Here's theorem 7, where we have the double integral is equal to, there's sine phi, right, and there's r squared, which stands for rho squared. So haven't forgotten that. So they are exactly the same. And now we're going to prove it. It was not proved in calculus 3. Okay, we were just given the formula, and then we tried to use it a little bit. So that's all we did in basic calculus. Now here we're going to prove it, and to prove it, first we're going to divide this thing into a bunch of subdivisions. And the subdivision is each one of these chunks. That was also done in basic calculus. The way this is described is the subdivision will be a tiny little chunk defined by r equal r0 to r0 plus delta r. Theta goes from theta 0 to theta 0 plus delta theta. And then lastly, phi will go from phi 0 to phi 0 plus delta phi. And there's a picture of this exact object in calculus 3, which I will show you right here. See, remember this thing? Okay, this thing is exactly, there is theta changes by del theta, phi changes by del phi, and rho changes, which is r, changes by del rho, etc. Okay, just this chunk right here is what I want you to pay attention to. So we're talking about this interesting looking chunk. And what are we doing here? Well, the book describes this chunk as you can obtain it by rotating the area A, the little area A, for only amount of delta theta. The same thing. as what we showed you before. Now the next job, what we have to do is calculate the the volume of that chunk. And what is the volume of that chunk anyway? Now, in basic calculus, we did not calculate the volume of that chunk, okay? And we just, we did something else there, that's simpler. But now we absolutely need to calculate the volume of that chunk. And so I need to show you how I did it, okay? The first thing, the knee-jerk reaction I had was I simply slapped on the formula for it. Okay, we'll integrate this thing for theta going to delta theta, right? Phi goes to delta phi, and r goes to by delta r, and just plug it into this formula, and then we'll call it done, which is what I did, and I came up with some formula. So this is the formula I came up with, which is what the book says. By doing the spherical integration, and I used the formula that was given to us in Calculus 3, okay, which was called the Fubini's theorem right here. And so that was my knee-jerk reaction when I saw that we need to calculate that chunk. So why don't we just use that formula and calculate because this theorem calculates this thing right away very nicely. But the problem, however, is once I did that, then I realized something is back in the day when we learned the Fubini's theorem for spherical coordinates, we never proved it. Right now, we are actually basically proving it. Okay, so we cannot use the theorem to prove the theorem. Therefore, I can't use it to calculate that little chunk. I gotta, do it in a more basic way, which is of course more painful. So then I had to. Once I realized that, then I was forced to do this. So here's the second method, okay, where we don't cheat by using what we're trying to prove our stuff. And so then I was forced to, then we have to calculate that little chunk. How are we going to do that? Well, I need to, if that is the case, I need to know what the volume of this cone is. That is, if you have some kind of cone, plus the top part, okay, the bottom is a circular cone, plus the top part was part of a sphere, I need to know what the volume is. And so after digging around somewhat, then, we know what the volume of a regular spherical cone is, right? The top part isn't as direct, but there is but we can calculate it without the Fubini's theorem by using the surface of revolution. Just spin that part of thing around, like calculate this thing. This is part of a sphere, okay? And then we just it continue to become a whole sphere, but we stop it at some point, and then we spin this around the x-axis and figure out what the volume is. That was done. We did that at one point in basic calculus. So there was an answer to it, which I copied right here because I wasn't going to do that again. And so I got the volume of the cone. That's the bottom part of this thing, okay, is that formula. The volume of the cap, that spherical object, after it's spun around, is called the cap. That volume is this thing. I copied that from the internet. It's a volume of revolution. So let's add it up. And then, and once I added it up, then, let me see, what else did I do? Maybe I should... So once I figure out what the cone with the cap is, then what we're going to do is let me think. Anyway, once I found that volume of this thing, it's like a snow cone, right? So once I found the volume of this thing, by adding these two objects together, I got this equation, okay, which ended up being equal to this. How do I need to know equal to this? Because I Googled it. I didn't want to, I could have done the trigonometric identity here, but I just Googled it and found this to be the answer. And then I did confirm it though. That is, I used the calculator and did the trig. The calculator did the trig identity for me. That is, this thing does indeed equal to this, okay? Because it says true. I used the Symbol Lab calculator to to prove this. Well, it doesn't take that much to prove it, but I didn't want to bother. Okay, and so that is done. And what this formula right here is the volume of the snow cone. We're still on the snow cone, but we finally come to a conclusive idea. So once we find this volume of the snow cone, remember we are still trying to calculate the volume of this chunk right here. Okay, that's what the snow cone is about. What happens is once we calculate the volume of the whole snow cone, then we can restrict it by calculating first we restrict it by calculating of the sphere. Okay, that is the sphere, the outside sphere minus the inside sphere divided by the outside sphere. Okay, that will give it the proportion in terms of spherical expansion. And then lastly, we'll multiply by delta theta divided by 2 pi, which calculates how much of going around is going. So when you multiply all this together, this is the sphere, this is the difference of R. This is the difference of delta, and this is the snow cone's volume. So when you multiply them all together, it will eventually give you this thing right here, which is the volume of that chunk. Okay, which also, as you notice, that is the same as the one we found before. The one before looks like that, and so does the one after. See, so all this work is just to show. Let me show it to you again. If you look at it more carefully, it'll make sense. Especially this part. Where's the part about? Where did it go? Right here. Okay, this is the critical part where you once you find the volume of a snow cone, then you find the proportion of it in terms of the sphere and in terms of the angle theta by multiplying the proportions, and that's how you get the chunk. Yeah. So okay, we finally got the chunk going, and once we have the volume of the chunk, where's my chunk? Okay, right here. And what I wrote is identical to this thing right here. That is equation 3. And from then on, then we can do some integration arguments and get out of calculating volume. So now that we're done with the volume, let's consider the law of the mean. Before we apply the law of the mean, let's see what it is. To refresh your memory on law of the mean on page 9 of the book, okay, the law of the mean is, on page 9, is if you have some function, the difference of the function, you can plug its derivative out, and it just and then that multiplied by just the difference of the values inside. Okay, so that's what you. So please memorize this for the next 5 seconds or so, and then as a result, we can do this. So this thing we'll take. See, this is the difference. Okay, we'll take the derivative of cosine, which is becomes minus sign, and then plug in the minus sign of phi, okay, and then of some value of phi prime, where phi prime is between phi 0 and phi 0 plus triangle phi. And so that there's that, and then of course the difference of the inside is delta phi right there. So we have those two in there, and the negative sign is taken care of somewhere in there. Please confirm that fact yourself. Now, similarly, this thing is we'll take the derivative of this thing, okay, which will become 3r, this function and this function, which becomes 3r squared divided by 3, so the 3 is gone. So we'll have r prime squared times delta r, where r prime squared is something between r0 and r0 plus delta r. So this is a neat application of the law of the mean here. All right. So that's that. And as a result of that, then we can plug everything in. This thing will be, which by definition is this. Okay. And then we can plug delta v in this part. So it equals to all this stuff right here. And all this stuff at this point, we're gonna. For now, then, we're going to think of them as not polar coordinates, but just regular, just any old thing, just some integration with these variables. Now, if we think of it that way, then then we can apply Duhamel's theorem on page 198, which I will show you the Duhamel's theorem, which right here. Okay, so the Duhamel's theorem says that if we have a bunch of stuff. Okay, we have the sum of F and then G, where there's stuff inside is not necessarily the same. Time del SK is the same as just integrating the whole thing. Now, this Duhamel's theorem is not 3D, but and what we're doing is actually 3D, but we'll just use it anyway. And yeah, we'll just apply it because we didn't prove this one anyway. This is just a 2D extension of the original Duhamel's theorem, which was only 1D. So we are just going to pretend that this thing works for 3D as well, okay, without proving it. And as a result, by Duhamel's theorem then, this thing is the same as the triple integral. The triple integral of just f and then x squared sine z dv is, when I say this thing, I'm referring to the summation stuff, all the stuff right here. Okay, and so please stare at this for a bit and stare at the Duhamel's theorem. And there is a slight catch in there, is that this has there are two variables here, r and phi, but f does have 3 variables, so we are taking there's yet another delta theta in here, but we'll ignore that fact and just apply Duhamel's theorem anyway, which will give us this thing right here. Okay, this thing on top right here. So the next thing we have to do is then we are going to, what is this? This is, we're going to apply theorem 5 on page 207 to say that this triple integral is the same as this iterated integral, which is what theorem 5 says, is the triple integral is the same as the iterated integral with proper ends, proper limits. And then so at this point we can change the xyz back to theta r theta phi. Okay, and because they're just dummies for integration, so it doesn't matter what we use, and then and we change it back, then the theorem is proved. And all this sounds a bit magical, right? So you might you might feel slightly odd about it. So please stare at this yourself. Okay, go over this theorem again yourself very carefully until everything makes sense to you, and just give the Duhamel's theorem some leeway. Okay, we haven't exactly proved Duhamel's theorem, we even stated it in 3D, but let's just say it works in 3D, 3 variables as well. So, and then think about the rest of it, what that means to like, such as interpreting this as rectangular coordinates. Okay, they're just dummies of integration, so you can change them if you want. But still, please spend some time thinking about this, and in general, is especially go through this proof of theorem 7 carefully and do the calculation of this thing right here. Okay, that I already did it, but try to do it yourself. Try to come up, now that you heard me how I did it, without looking at what I showed you, please calculate the volume of that chunk yourself to make sure it comes out. All right, so that is theorem 7. So next, we are going to find the volume of some cylinder by use of spherical coordinates. Now, we all know what the volume of the cylinder is, right? The volume of a cylinder is simply pi a squared times h, which says right here. But please use this, convert everything into spherical coordinates, which is done right here. And to do that, you have to cut the region in half, half across to have 2 sets of integration in order to make the conversion work. Now, so please do that yourself. I know that sounds extremely tedious, but I did it, and it's a somewhat decent practice of using spherical coordinates. So I did it here for your reference, but please do it yourself as well, just to get a feel for it. Yeah. Which is it's not that much fun. Okay, proving theorem 7 is much more fun. But in math, some parts are more fun than others if we just have to deal with that. So for homework, please do on page 212. Please do problems 1, 2, 3, 4, and 12, 13, 14. And when you get back, I will talk about it. So let's look at problems 1, 2, 3, and 4. But first, I want to emphasize that, that these problems mostly have to do with doing conversions that I showed you earlier. You just have to pay attention to these conversion rules between spherical, rectangular, and polar coordinates. So once you pay attention to that, then everything comes out pretty readily. Now, so problem 1, the moment of inertia of some sphere, that is pretty standard, okay? So that's that. And problem 2 is the same thing of a cone or something. Anyway, so that's what I got there, okay? And then problem 3 is some gravity force of, yeah, something. I don't remember what, but anyway, you just, but the only trick is we are forced to do it in cylindrical coordinates. But if you have to plug in the right thing and do a little bit harder integration than necessary, but eventually come up with the right answer like this. Now the answer in the back includes rho, which it means density, but we don't care about the density. We just assume the density is average. Is 1, I mean. Okay, so that's that. Problem 4, I think, is the same as problem 3, except doing it in spherical coordinates, which is a bit faster, as you can see. Yeah, it's more convenient, and it gives the same answer. So next, let's consider problem 12, which says we're calculating, what are we calculating? The region defined by inequalities with those values defined. Okay, so let's do that. If that is the case, I have it written down here. The hard part is just to do the conversions, right? That's problem 12, which is the same as problem 13, I guess. So what happens is we do the conversions here, and so on. And once we do the conversions, we get these equations, which I then typed into the Desmos calculator. Even without typing in, you know what it is, some kind of sphere, okay? And so here are our spheres. We have, here's the conversion formulas into rectangular coordinates. So the b equal to 3 is the bigger sphere, and then the a equal to 1 is the smaller sphere, and that is our region, is the big sphere minus the small sphere, so the space in between. I draw a small hole there so we can see inside the sphere better. Okay, there's actually no hole in reality. So that is problem 12. Look how beautiful it is. And it's, yeah, in my day, you couldn't do anything like this. And so I rather enjoy doing this kind of thing because it just makes it so much more pleasant. And then problem 13 is plotting the exact same thing, except that now we're going to treat everything as rectangular coordinates. So then I have theta in the x-axis, okay, phi in the y-axis, and r in the z-axis, and then I plot r equals to b cosine theta phi, b equals to 3. And then this is r equal to a cosine phi, a is 1. So then I got this graph by the time everything is done. And this surface, the green surface, is where phi equal to 0. Okay, and so this thing, these are the same things, just in different coordinates. As you notice, the red sphere got turned into that surface, and the gray sphere got turned to the other gray surface. And then, and you might wonder, what's the green surface? The green surface collapsed over here at phi equal to 0. Okay, so the whole thing is down there. So that's how the two surfaces, well, at least I think it did. Let me think, is that actually true? Maybe, let me think first. Sorry, I said that wrong, okay? And this is where the two surfaces touches, right? So that's where they meet, right here in one point, and this becomes a line. It's not here. That is, I don't know what that is. We'll think about that later. That is not that important. My point is, yeah. So these two are the same thing, but it's plotted in different coordinate systems, and so then they look completely different. And it's just something cute to see in this type of problem. So that's problem 13. And finally, problem 14. And not much happening with problem 14. We just have we just treat these things as rectangular coordinates. The limits, right? If we exchange it, you just well, exchange it like that. That is all there is to say about it, really. And so, and that marks the end of this section.